Welcome back to Environmental Science 446, 546. This course is Drinking Water and Human Health. Today we're going to go through lecture number 8. Topic today is Drinking Water Standards. You have a handout in your packet that also covers drinking water standards, so it's nice supplemental material for you. If you get your drinking water from a community water system or a public water system, you must realize that regulations exist to protect the quality of your water supply. On the other hand, if you get your drinking water from a private well, there are no regulations. The Safe Drinking Water Act does not cover you. Consequently, if you get your drinking water from your own private well, it's basically user beware. Again, if you get your drinking water from a private well, there are some general guidelines, but they're unenforceable. You are responsible for protecting the quality of your water. In Lecture 8 and 9, we'll talk about the drinking water standards. I'm splitting them this way. Today we'll talk a little bit about national drinking water regulations. We'll talk about the primary standards, and today we'll cover the organic chemicals and the inorganic chemicals. And in lecture number 9, we'll cover microorganisms, turbidity, radionuclides, and secondary standards. If we look at national drinking water regulations, first of all, EPA regulations are subdivided into two categories. And we've already talked about these. You were introduced to these two categories in the last two lectures. The first category are primary drinking water standards. And the second category are secondary drinking water standards. When we talk about primary drinking water standards, there are specific maximum contaminant levels based on health-related criteria for contaminants that have been shown to adversely impact human health if they're present in large concentrations. Except for microbes and nitrates, water that exceeds listed MCLs does not pose an immediate threat to public health, but these are guidelines that over the long term there may be some problems. So let's take a look at categories for primary drinking water standards. The categories we're going to cover today are organic chemicals and inorganic chemicals. We have other categories, but we will cover them in lecture number 9. So in lecture number 9, we'll talk about primary drinking water standards for microorganisms, primary drinking water standards for turbidity, and then finally, primary drinking water standards for radionuclides. Later on in the course, we'll have specific lectures in each of these categories, so we'll spend a lot of time talking about them. Okay, so let's start with the first category today. Let's start with organic chemicals. If we look at organic chemicals, there's basically three categories of organic chemicals that are regulated. These include the synthetic organic chemicals, often abbreviated as SOCs, the volatile organic chemicals, often abbreviated as VOCs, and the trihalomethanes, which are often referred to just simply as our THMs. As more research is done, the numbers of regulated chemicals in each of these three categories is likely to grow. So we started out with very few synthetic organic chemicals regulated back in 1974 when the Safe Drinking Water Act was passed. That number has increased substantially over the past 40, 50 years. So they're likely to grow. So let's start out with the first category of organics, the synthetic organic chemicals. Later on, we will have a couple lectures talking about specific synthetic organic chemicals, but for now, let's just talk about the general category. So for synthetic organic chemicals, these are chemicals that are made probably in a laboratory by humans. They're human-made chemicals. Many of these chemicals are toxic to living organisms. They were designed to be toxic to living organisms. They may be pesticides or things like that. So part of their utility is they are toxic to certain organisms. These synthetic organic chemicals are used in the manufacture of many agriculture and many industrial products. And there are thousands of chemicals in this category, very few of which are regulated now. Over the long term, you're going to see more and more of these synthetic organic chemicals being regulated as far as water quality. Let's take a look at a few examples of some synthetic organic chemicals. Let's start with the table. On the left column, we'll list the contaminant. In the middle column, the health impacts. And then finally, what is the MCL for this particular chemical? So let's just look at three common chemicals that are SOCs. Our first is aldicarb. Aldicarb is used in agriculture. It's an insecticide. The impact of aldicarb, if humans come in contact with it in sufficient quantities, is that it has a negative impact on our nervous system. Basically, we have an MCL. EPA has a MCL established for aldicarb at 0.0003 milligrams per liter. They have an MCL goal of 0.001 milligrams per liter. So they would like it to be lower. The goal would be lower, but right now it's regulated at 0.003. And remember, there are thousands of synthetic organic chemicals. Most of them are unregulated in water. I'm just showing you an example of three different chemicals that are SOCs. Next chemical is chloridane. Chloridane is also an insecticide. Laboratory tests with animals have shown that it's a carcinogen, which means it can cause cancer in laboratory animals. It would be implied that human exposure to high levels of chloridane might also cause cancer in humans. We have an MCL established for chloridane of 0.002 milligrams per liter, but the EPA has an MCL goal of having no chloridane in drinking water. And then finally, let's look at a third chemical for today's discussion. Carbon tetrachloride is an example of a synthetic organic chemical. Carbon tetrachloride is used for several things. It's a cleaning agent. It's an industrial waste. It's present in many areas of our ecosystems. Research has shown that with laboratory animals, carbon tetrachloride can cause cancer in laboratory animals. Thus, we suspect that exposure to large concentrations of carbon tetrachloride to humans or long-term exposure may pose a risk of cancer, so it's regulated. There's an MCL of 0.005 milligrams per liter, and the EPA has an MCL goal of 0. So that's our first category, synthetic organic chemicals. There's thousands of chemicals in this category. I gave you an example of 3 of them. Very few of them are currently regulated, but with time and research that shows that some of these chemicals may adversely impact human health, we should expect to see MCLs for drinking water for more and more synthetic organic chemicals over time. Let's go to our second category, the volatile organic compounds, or we refer to them as VOCs. These are synthetic chemicals. These are chemicals that at room temperature will vaporize into the air. We have a lot of VOCs that we use in everyday life and in industry. We use VOCs as degreasing agents. We use them in glues, in dyes, in paint thinners, and there are some pesticides that are actually volatile organic chemicals. Again, let's take a look at 3 chemicals that fit in this category. Later on, we'll have a couple lectures that deal exclusively with VOCs. Again, let's take a look at a table. The same structure, contaminant is on the left side of the table, the health impact, and the MCL for this chemical, and the MCLG, or the goal, what EPA would like to see. Let's start with benzene. Benzene is a widely used industrial chemical. It's regulated as far as drinking water is concerned because laboratory studies have shown that large exposures will cause cancer in animals, and there's the implication that the same would occur for humans. Because of that, we have an MCL of 0.005 milligrams per liter, and the EPA would like to have a goal, an MCL goal of 0. They'd like to see none of this at all at any concentration in water supplies. Let's look at a second VOC, trichloroethylene, or often abbreviated as TCE. This is a waste product from dry cleaners. It's a product from pesticides. It's found in paints. Again, it's regulated because research has shown that laboratory animals exposed to high concentrations of TCE may develop cancer. And again, the implication is humans are biological organisms. If they are exposed to TCE over the long term or high concentrations, they also may develop cancer. So we have an MCL of 0.005 milligrams per liter, and the EPA has a goal of 0, a concentration of 0 in our drinking water. And a third chemical, let's look at vinyl chloride. Vinyl chloride is a component of many things. PVC pipes are an example that contain vinyl chloride. Again, laboratory research has shown there is a risk of laboratory animals getting cancer from exposure to vinyl chloride. And again, this would mean that the implication is that humans, long-term exposure or high exposure to high concentrations may result in cancer. So it's regulated. It's a drinking water contaminant, an organic drinking water contaminant, and we have an MCL of 0.002 milligrams per liter and a goal of having nothing in our drinking water. Again, we'll spend a couple lectures talking about the VOCs when we get to the organic chemical portion in this class. And finally, for our organic chemicals, we'll take a look at THMs. THMs are basically created in water as a byproduct of chlorination. We use chlorine to kill microbes in water. Oftentimes we treat water in wastewater treatment plants with chlorine to kill pathogens. So you get a reaction. It's a byproduct reaction. What happens is if you have any organic chemicals in the water and you add chlorine to it, you can get the chemical reaction and generate a THM. There are several THMs out there. They include things like chloroform, bromoform, bromodichloromethane. Those are examples of THMs. And as you would suspect, they're regulated because they might adversely cause problems with human health if humans are exposed to high concentrations. Let's just look at one example using the same type of table. Oftentimes in the laboratory we measure total THMs, so we're going to combine all the THMs together here. THMs that come from the chlorination of water, things like chloroform. Laboratory research has shown that THMs, exposure to THMs, may cause cancer in laboratory animals, and we draw upon this just to extrapolate that humans that are exposed to THMs over the long term or high concentrations may also be at risk of cancer, so we have an MCL. THMs are regulated. We have an MCL of 0.1 milligrams per liter. EPA has a goal of having nothing in there. We'll talk about THMs in a little bit more detail as we go through the lectures of this course. So basically, I've covered the category of organic chemicals. It's a huge category. There's thousands of chemicals that fit this category, but right now we only have several dozen chemicals that actually have MCLs. established by EPA. Probably over time, many more of these chemicals, organic chemicals, will be linked to adverse impacts on human health, and MCLs will be developed over the time period. And remember, the amendments to the 1974 Drinking Water Act, passed in 1986 and 1996, require EPA to keep looking at chemicals down the road to see if they cause problems in drinking water. And many of these chemicals that EPA is evaluating are these organic chemicals. Okay, let's move to the second category of chemicals covered by drinking water standards, and these are the inorganic chemicals. This includes a huge number of chemicals. Several of these chemicals are of public health importance, and these are the chemicals that you probably have heard about. These inorganic chemicals can be found in drinking water as a result of a lot of things. First of all, natural processes. The aquifers, or the geologic material in which the water you drink that's located, may naturally have some inorganic chemicals in there. There might be environmental factors that cause these inorganic chemicals to be in your water. There may be human activities that cause problems, that may cause the release of these inorganic chemicals into our drinking water. We have some processes, industrial processes, that release maybe lead or mercury into the environment, and if the lead or mercury finds its way into a water source that we eventually use for drinking water, that may be the reason why we regulated it. So let's take a look at a few inorganic chemicals. Again, we'll cover these in a lot more detail as we move through the course. Again, the same type of table. We've got the contaminant listed, the health impacts of the contaminant, the MCL that has been established by EPA, and the MCLG goal, or what the EPA would like to see in water. Let's start out with the probably the gorilla on the block, inorganic contaminant called nitrate. Nitrates come from a whole host of human activities. Some nitrates are naturally present in the environment. Nitrates can come from fertilizers, from sewage, from animals, from the soil. There's a lot of ways we get nitrate into water, which eventually becomes our drinking water. The negative health impact of high levels of nitrates in drinking water is a condition called blue baby syndrome. Blue baby syndrome occurs in children less than 6 months old. Because of the adverse impact of nitrates on humans or infants less than 6 months old, remember, a vulnerable part of our population, there is an MCL established, and that's 10 micrograms per liter, or 10 parts per million nitrate nitrogen per liter, or 10 parts per million nitrate nitrogen, not per liter. We'll spend 2 days talking about nitrate in detail in this class. So here's an example of an inorganic chemical. Let's look at another one that I've already alluded to when we talked about the amendments to the Safe Drinking Water Act, is lead. Lead's primarily gets into drinking water because it's a component of pipes and solder, which holds pipes together, and other fixtures. Lead, when humans are exposed to it, can attack the nervous system, can attack our kidneys, and it is particularly toxic to infants. Because of this, we have an MCL established for lead, and that MCL is 0.15 milligrams per liter. We'll spend some time talking about lead in this course. Let's look at a couple inorganics that you may be a little bit more familiar with. Arsenic. Again, we'll spend an entire lecture on arsenic this semester. Arsenic can get into drinking water simply based on the geologic material where the water resides. We've used pesticides in the past that contain arsenic. Arsenic just does not decompose, so If we used a pesticide, an arsenic-containing pesticide 100 years ago, it would still be around and might leak into the water. A lot of the industrial mining processes involved in smelting metals generate arsenic, and there are some industrial wastes that contain arsenic. We don't want arsenic in drinking water because it has a negative impact on the nervous system in humans, and we'll talk about this in quite a bit of detail this class. Consequently, we have an MCL established at 0.05 milligrams per liter. This value has been changing. It's been lowered over time, and we'll talk about the science behind the reason why the MCL is often looked at as being 0.01 milligrams per liter now instead of just the 0.05, which the EPA used to use. Let's look at a couple other inorganics for a couple minutes. Mercury. Mercury is used in industrial processes. Mercury is present in a lot of rock formations. It also was a component of many fungicides in the past. Anytime these wastes leak into water, they can be long-lived because mercury doesn't decompose, and it can get into our drinking water supply. Research has shown that mercury adversely impacts a person's nervous system and can damage kidneys. Consequently, we have an MCL for mercury of 0.002 milligrams per liter. Look at a few other inorganics. Cadmium. Cadmium is present in certain rock formations. It's a product of making phosphorus fertilizers. It's a product of metal finishing processes. We know that at high concentrations, cadmium has a negative impact on human kidneys. Consequently, we have an MCL for cadmium levels in drinking water, and that MCL is 0.005 milligrams per liter. As you look at this table, one thing I'd like you to take-home message is EPA has an MCL, but they don't have an MCLG. They don't have a lower number for a goal because in some situations, based on where the water comes from, it's impossible or unachievable to get these values much lower than their MCL. Let's continue with a few more inorganic chemicals. Fluoride, an inorganic chemical. Fluoride is present in many geological formations. It's a product or a waste product of smelting processes involved in metal mining. And sometimes we put fluoride directly in drinking water to prevent tooth decay. A little bit of fluoride is good for human health. Too much fluoride is very bad for human health. So health impact is dental. A little bit of fluoride in drinking water basically prevents cavities. Too much fluoride in drinking water causes bones to break down and has negative impacts on a person's skeletal system. So we have an MCL for fluoride of 4 parts per million, or 4 milligrams per liter. And as you would suspect, we have a lot of communities that actually add fluoride to the water. It's not common to have too much fluoride naturally in the water, but we have an MCL for that. Another inorganic chemical is selenium. Selenium is present based on geological processes. You find it just in some rock formations. It's a product of mining, a waste product through the mining process and the smelting process. So there are areas where you could have abnormally high levels of selenium in water. Research has linked high levels of selenium in water to liver damage. Consequently, because it's an adverse impact on human health, we have an MCL for selenium of 0.05 milligrams per liter. You'll all have a chance to work with some of these inorganic chemicals as we move through the semester. But I'd like to reiterate that we will spend special time on nitrates, lead, and arsenic. We'll have lectures devoted to those particular 3 inorganic chemicals. Let's add one more inorganic chemical to our list. Let's add asbestos. Asbestos, we usually think of as a contaminant that's airborne. Certainly, there's a lot of health concerns about airborne asbestos, which is a component of older types of insulation. But we can also get asbestos in drinking water because of geological processes. There's some rock formations that are just naturally high in asbestos. We don't want asbestos in our drinking water because there's a linkage between asbestos and cancer. Consequently, we have a drinking water standard for asbestos in water, and that happens to be 7 fibers per liter. And we'll talk about that when we talk about inorganic chemicals in more detail. So we have some other primary standards for some other inorganic chemicals, and I just want to list them right now. Things that at high concentrations may adversely impact human health, and we have MCLs for them. We have an MCL for barium. We have an MCL for chromium. We have a concern about copper, although an actual value is not really set in stone right now, and we'll talk about that when we get to copper. We have an MCL value for cyanide. High levels of cyanide, as you would suspect, are not good. They're particularly not good in drinking water. Same thing with nickel. So these are just other inorganic chemicals that we actually have primary standards for. So in today's lecture, we introduced drinking water standards. We have 5 categories of drinking water standards, and the first 2 are organic chemicals and inorganic chemicals. We have 3 other categories, and we'll cover them in Lecture 9. Those 3 other categories include the microorganisms, they include turbidity, and they include the radionuclides. Thank you for your attention today.